Power generation. Okay? Put bluntly, without electrical power, we probably wouldn't survive as a race. Not these days. Everything we do, we use electrical power for. And what we use it for is to convert energies and transmit energies from one place to another. Okay? Electricity in itself doesn't do us a lot of good, except when we use it for lighting and it just creates warmth and light. However, the majority of electricity out there is used to do mechanical work. Okay, like turn motors and turn big pumps and that sort of stuff. Now, to do that, we have to take energy, typically carbon fuel, like oil, coal, that sort of stuff. We release the energy that's embedded in that stuff by setting fire to it. We take the heat, we use the heat to create electricity, and then we use electricity to transmit that energy to where we want it. Okay, so the whole reason for electricity really is to transmit energy from one place to another where we can use it to do what we need it to be done. Now, if we look at the basics of electricity, it's based on the relationship between magnetism, right, and the atom. Now, the atom is what makes up everything in this world. Okay, but an atom is comprised of protons, which is the nucleus, the center part, and electrons, which are the small things that rotate around the nucleus. Okay, now those electrons can be closely coupled, or they can be loosely coupled. In other words, if they're very tightly coupled, there's a very strong bond between the two parts, between the protons and the electrons. If it's loosely coupled, there's a very loose bond between the two. Okay? Think of the planets going around the sun. The planets closest to the sun are very much under the influence of the sun's gravitational field. But the planets right at the edge of our solar system are much less influenced by the sun's gravitational field because they're much further away. Now, in our case, right, the electrons in some materials, like copper wire, for instance, is one of our favorites, right, and a conductor, right, those electrons are quite loosely coupled. So by putting a charge across that piece of copper wire, a magnetic charge, across that, we can energize the electrons to move from one proton, from one atom to the next. So we can convince them to flow in one direction. But obviously, if an electron leaves an atom and goes to the next atom, another electron has to take that electron's place. Okay? So we find that what we have to do is have a complete circuit on that copper wire, so that the electrons flow around the copper wire, but there's always, every hole is always filled by an electron. Okay, so that's why in electric current we have to have a continuous loop. We have to have a circuit as such for it to work. Okay, now, fundamentals of electricity is that there are three parts of it. We have the actual electrons themselves. The electrons flowing constitute the current. Okay. Then we have what's called the volts. The voltage is what pushes the current around the circuit. Okay? And then we have the resistance of the actual circuit. That's the reluctance of the electrons, or the energy that's required to make the electron leave one neutron and jump to the next one. Now, to give you an idea how it works, if you think of a syringe filled with water, okay? The water is the electrons. Okay? And at the end here we have a nozzle through which the water has to pass. And that is the resistance to the flow. And at this end we have a plunger, which is where we apply our voltage. So now, if I apply a force to the plunger, it moves down, it forces the water through the resistance, and the water comes out past the nozzle. Okay? Now, the harder I push, the further that water and the more water comes through that nozzle. So, voltage is what does the pushing, resistance comes from the nozzle, if you like, and the current is the water that passes through it. The same thing applies to electricity. The voltage pushes the electrons along a resistive conductor. So, taking that one step further then, if I take a piece of wire and coil it into a loop, like so, and bring it to a point here, if I then put a load across there, like a little light or something, and spin the wire around inside a magnetic field, what happens is, as this wire rises across that field, it creates a potential difference of voltage that wants to push the electrons in one direction. Meanwhile, this one is going the opposite way through the south pole, and that assists to push the electrons in the same direction as this one does and make them go round. That way then we have a flow of electrons through the circuit. Okay? Now in this case here, when that point gets to the top here, it's halfway between the two, so there's no current. As it starts to move down, okay, it starts to generate current again, but in the opposite direction to what it was here. That means the current here goes from positive that side to positive this side, and back to positive that side again. In other words, it's an AC current. If at some point I could take this at the top and switch these 2 points around, then the current would always flow in one direction, and that would be a DC current. Okay. So, to do that, I have to rotate that piece of wire inside a magnetic field. To do that, I have to have some form of mechanical energy. Okay? So, that coil of wire inside a magnetic field we call a generator. And it's an electromechanical device because it needs to be mechanically turned and it will generate electricity. Okay. Now, one of the most common ways to do that is by what we call a heat engine. Some method of transferring heat taken from fuel, okay, and turning it into mechanical force. Right? The other way of doing that is, rather than taking the heat, is to use the kinetic energy of natural stuff like wind and water. Wind and water, when they flow, have a lot of built-in energy, and if we use blades and can extract that energy, we get again the mechanical force required to turn the electromechanical generators. So, when we are using electromechanical, which is majority of the time, I mean right up there in the high 90s of the time, okay, we need some form, doesn't matter where we get it from, of mechanical energy to rotate the generator to give us electricity. Okay. Now, it can be generated chemically by using two different types of materials put together, shine the sunshine on them, and that causes a voltage difference between the two. Right? And things like batteries and that sort of areas. But typically they tend to be fairly low power and low volume. Okay? The majority of stuff, the big stuff that produces enough power to run cities, is done by electrical mechanical generators. Okay. Now, here's a fundamental generator, and this one is a water turbine. Okay? In this one's case, let's look at the size of this now. There's a little figure of a guy there, average humans. You can get some impression of the scale of this. Down here we have a turbine, which is basically a big propeller in this case, over which we pass water. Water comes along here, past these gates, and down across the propeller and out to the river. Hence the propeller turns. When the propeller turns, it turns this magnet in here inside a field of copper wire. Okay? So that rotor rotating inside the field causes a magnetic field to rotate through these copper wires and create power. Now in this case, the picture we've shown here is a water turbine. It could be done by a steam turbine, and it could also be done by internal combustion engines such as a gas turbine or a diesel engine.